Alright, so what we'd like to look at now is we'd like to look at two waves interacting in the same medium. So when they interact, what we're going to say is we're going to say that these waves superimpose on each other, or they're going to interfere with one another. And if they interfere with one another, we're just going to say that interference is occurring. So what we generally like to ask is, and keep in mind, this effect's only temporary, because as the waves pass through one another, the shape is going to change slightly. But if we want to look at the shape at a certain time when two waves are interfering with one another, we can use that whole idea of the principle of superposition to look at the shape of the new wave. So what it's saying is that the displacement of the combined pulses at each point of interference is the algebraic sum of the displacements of the individual pulses. Basically what you're doing is you're adding the amplitudes together at that point and checking out what the new amplitude is. Being mindful that things above equilibrium will count as positive, things below will count as negative. And we'll look at that in a little bit. So here we have kind of two pulses approaching one another. So we've got A and B, they're approaching one another. As they start to overlap, you'll kind of see, we still want to show our original waves because they haven't gone away. But what you're going to notice, what you will see is the combined effect. When they overlap, you will lose their originality while they're overlapping. All you'll be able to see is that combined effect. So we have that overlapping here, so we can see this pulse, and then we see this pulse moving through. And then as these waves fully pass through each other, then we can see the two individual waves moving past each other. So we kind of have two possibilities that's going on. We can either create a wave with a greater amplitude, or we can create a wave that is smaller in amplitude than the individual waves. So if we combine waves together and we make one with a larger amplitude, this is what we refer to as constructive interference. If we combine the waves together and we make smaller amplitude, this is what we call destructive interference. We also have that really special case if we combine two waves together that have zero amplitude, so kind of like the wave disappears entirely. This is referred to as complete destructive interference. So a good example of destructive interference is for those of you that wear like noise canceling headphones. What your headphones try to do is they try to create sort of the opposite wave so that when they combine together, it's almost completely canceled. So like for example, if this is the sound wave, and say it looks a bit like this, what your headphones might do is they're going to try and create a wave, maybe it looks a bit like this. Maybe its amplitude is not as great, but basically it's trying to create a wave sort of opposite to this, so that when we add the two together, what you hear, you might hear something a little bit like this. Like just an ever so slight wave. It's probably not going to be perfectly canceling, but you will notice that reduction in amplitude. That's what your headphones are trying to do. They're trying to generate this wave to reduce the amplitude of that sound as much as possible. So yeah, we have constructive interference here. You'll see our two pulses overlapping to make a bigger wave. And then for destructive interference, you'll kind of see those two pulses combining to make a slightly smaller wave. So again, we can use that whole principle of superposition to sort of figure out what the resultant wave is. So we're going to say that our upright pulses, we'll call them as having a positive amplitude. Inverted pulses, they're going to have a negative amplitude. So we want to sketch the resultant wave when these waves happen to superimpose or interfere with one another. And then we're asking what type of interference this is. So these two waves are going to eventually approach each other. So when they approach each other, we want to find the amplitude of the new wave. So we have an amplitude of +1 meter. Because it's positive, it's above the equilibrium. And then we have this wave here with an amplitude, we'll call it -2 meters because it's below the equilibrium. So our resulting wave is going to have an amplitude of -1 meters, or we're just going to say it's a meter below equilibrium. So what's actually happening, and I'm going to sketch the whole thing out. So we have our first wave here. So we're looking at when they overlap. So that's this wave traveling this way, and then we also have our second wave here that happens to be a little bigger. So what's happening is we're sort of having a bit of a cancellation effect. So this part up here is going to cancel a little bit of this out. So what we're left with, so the resulting wave in this case is just going to look a little bit like this. So we're just going to have a wave pulse, it's inverted, it's going to have an amplitude of 1 meter below the equilibrium. And because we've created a wave with a smaller amplitude, this is destructive interference. And that's all we mean by the superposition, like applying the superposition principle. We kind of look at a point in time, we add the two amplitudes together, keeping positive above, negative below, and then the resulting value will give us the actual amplitude at that point in question when they're interfering or when they're superimposing. So the last thing we just want to kind of tie up here for theory purposes, it has to be with standing waves and resonance. So when we're dealing with standing waves, you're going to have two waves. They have identical wavelengths and identical amplitudes. So they are going to be the exact same waves. They are just going to travel in opposite directions. What we'd like to do is we would like to look at the actual interference pattern that is produced through the principle of superposition. So again, when we have two crests or two troughs occupying the same position, we're going to have constructive interference. So we're going to say at these points the waves are in phase. If we have a crest occupying the same spot as a trough, or a trough occupying the same spot as a crest, so one above, one below, this is going to be a case of destructive interference. We're going to say the waves are out of phase. So what we're looking at here is we're kind of looking at these two waves, this one in blue and this one in purple, so A and B. What's going to happen is they are going to start to move past each other. So you'll notice that they have the same speeds, they have the same amplitudes, and they have the same wavelengths. So what's going to happen is that as these waves advance a quarter of a wavelength in their respective directions, so as this purple wave moves a quarter wavelength to the left, this wave here moves a quarter wavelength to the right, we're going to notice an overlapping of the amplitude. We're going to notice the amplitude of this second wave, wave B, is going to, this crest of wave B is going to meet with the trough of wave A. So this red is meant to show you the effect of this. This is going to be destructive interference. Now, both waves are going to advance another quarter of a wavelength. So what's going to happen this time is the my goodness, I'm getting caught in my words. The crests of both waves are going to meet up at this point, and the troughs of both waves are going to meet up. So what we're going to do is we're going to produce these larger waves, or we're going to produce constructive interference. If they advance another quarter of a wavelength, we're still having crest meeting trough, trough meeting crest, so we're going to produce destructive interference. And then as we advance another quarter of a wavelength, we'll see that constructive interference. Then another quarter wavelength will have destructive interference. What you should notice is you'll notice these points here, these black dots. These are referred to as nodes. So at these points, this is where you'll notice that there's always destructive interference, because the wave is not moving. Nothing is changing at this point. What you'll also notice is that it looks like the wave is kind of flipping and flip-flopping. Like up here, it's above, and then it's going to go below. What you'll notice with the standing wave is it kind of looks like the crest is always kind of oscillating between crest and trough. So like here, it's going to kind of look that as the wave moves, this is going to move back and forth. What it actually looks like is it looks like the wave is staying perfectly still. Like it looks like these points are anchored in place, but it looks like the wave, like, if you look at a crest, then it's going to switch to a trough, then it's going to switch back to a crest. Like it's going to kind of look like it's continuously flipping. So this type of wave here, it's really special. These are referred to as standing waves. So these points where we have maximum amplitude, these are referred to as antinodes. These black dots here where the wave is always experiencing destructive interference, these are what we refer to as nodes. So these are our nodal points, these are our antinodal points at maximum displacement from the equilibrium. So whenever we have a standing wave, each successive node is going to happen every 1/2 of a wavelength. So like if I look on my diagram here, all of these nodes are going to be spaced out by 1/2 of a wavelength. Each successive antinode is also going to occur at an interval of 1/2 a wavelength. So if I look at the distance between these two antinodes here, these are going to be, these aren't successive antinodes, sorry. If I look at the distance between these two antinodes here, that's also going to be 1/2 of a wavelength. So that's just something to keep in mind in terms of the theory mechanics of this.